Look at that. It's kind of anticlimactic at this point, isn't it? Well, we get to spend some time on gas chromatography, so we get a couple lectures on it, which I'll be giving. Many of you know me, I guess. My area of research is flavor, and so I'm interested in the chemistry, the analysis of volatile compounds. There's really nothing better than gas chromatography for that type of analysis. So anyway, we'll go through it. We'll talk a little bit about the hardware, a little about the process itself, and then also some time on applications. So what do we use it for? And so I've got a tough question for you. What do you think the mobile phase is? You betcha. Yep. So you've been working. Have you done any other types of chromatography, basic chromatography? Okay, so you've been working with liquids as the mobile phase for that process. Again, this is a gas. So we have to turn our compounds into a gas, into a volatile compound, so it can travel with that mobile phase. What's our stationary phase in this case? Again, you've worked with different stationary phases then, or at least listened to them. What do you think the stationary phase would be on something like this? You know, they talk about gas liquid chromatography oftentimes, which suggests it's a liquid. And yet, if we fill a column with liquid, it's going to flow out. So we attach it. We typically chemically attach what might be a liquid to the inside of our column. So we have a gas flowing through a column that interacts with the stationary phase, a coating on the inside of that column. You'll hear different names when people talk about this type of chromatography. You might hear people saying gas liquid chromatography, and it really isn't a liquid when it's bonded onto the column. So that's really not quite right. Oftentimes people will simply talk about GC, gas chromatography. Some countries, especially in Europe, talk about high resolution gas chromatography. And really it's all high resolution gas chromatography today. So I kind of like just GC, gas chromatography is the way out of that one. But they all are the same type of process. They all involve the same process. Really, lots of applications. This technique is really broadly used in the food industry and analytical laboratories. Look at what we can do. Some of you had a lab on fatty acids, or all of you at this point? Half. Okay. So half of you have done fatty acids, so you'll know certainly that's one of the primary uses. We're interested in what's the fatty acid composition of a triglyceride. How do you know? Gas chromatography is the way to do that separation. But you can do things like cholesterol. If I'm interested in gas flushing a container, I want to make sure all the oxygen's out of that package so my product doesn't oxidize. How do I measure what's inside of the package? Have I done a good job of flushing all the oxygen out? Want to measure oxygen? We can do it by gas chromatography. We may be using solvents, and are they pure or aren't they pure? So solvent purity. We can analyze water, determine you've done moisture content, right? Not yet? Okay, I won't ask anymore. Water analysis, we can do that by gas chromatography. You may be doing Carl Fisher where you actually put anhydrous methanol, you're sampling anhydrous methanol, the water goes into the methanol, and you titrate it. We could just as well measure it by gas chromatography. So water, alcohol content in food, sugars, amino acids, vitamins, pesticides, food additives. You can kind of go down the list there and look at the diversity. In some cases, there might be a better way to do it than gas chromatography. Our compound must be volatile, and oftentimes what people do is they take something like a sugar, which is not volatile, they make a chemical derivative of it. They take care of all those hydroxy groups, and then they will do gas chromatography. So oftentimes, you know, you might be an easier way to do it, but the equipment is around, it's available. and people tend to use it broadly. From a historical standpoint, when did chromatography start? I guess there's a couple of different options on dates that it starts. Separation of dyes in 1850, separation of plant pigments in 1906. So chromatography's been around for a while. It's about 150 years, more than 160 years since certainly we started here. And so we have a long history. In 1941, the first paper was published on gas chromatography. It was a theoretical treatment. Gosh, we may be able to do chromatography in the gas phase, which was absolutely revolutionary. It took 11 years to go from theory to practice, and the first gas chromatograph came into being. This first gas chromatograph was rather clumsy, rather awkward in the sense that we could separate these compounds like fatty acids, separate them one from another, but we had no means of detecting them. You actually trapped them in a solvent and titrated them. That gets kind of boring if you got 50 compounds to sit and titrate and capture each one. So we really look at 1954 is when our thermal conductivity detector came into being. Now we started having a detector, and so we could do our separation, we could do our measurement. And it's interesting that this is a mature technique, and it was mature probably 25 years ago. By that, I mean they've reached the theoretical maximum. And theoretical says we can get this quality of separation. We were there 25 years ago. You're not going to find any revelations in this field anymore, or in the last 25 years. Cuter equipment, more expensive equipment, maybe more convenient equipment, but we don't have any better separation or any better methods of detection. So it is a mature science. Liquid chromatography is still evolving, and that'll be evolving for some time. That will keep getting better. Gas chromatography, like I say, maybe more convenient, something, but no better in terms of separation. So we'll talk about the process of gas chromatography, and then we'll get into a little bit about the hardware of this technique. So what's our process? Sample is vaporized if it's not already a gas. So we need to turn it into a gas. So we vaporize it in one way or another. Typically, we'll vaporize it through heating. So we'll inject our sample into a very hot area. It goes poof, becomes a gas, and it moves with our mobile phase. So our mobile phase goes ahead and drags our sample through a column. It interacts with the stationary phase to various extents. Some compounds will love that stationary phase. They kind of hang around for a while, move slowly. Other ones will have no affinity. They go right with that mobile phase. And so we really look at an interaction between where your compounds want to be in the gas phase or interacting with our column inside, the inside of the column, that coating that's there. And hopefully separation occurs. I suppose I should put hopefully in there. We have, over 6 million compounds that have been identified by American Chemical Society. So we're kind of optimistic when we say that out of the 6 million, we separated all of them, and that's absolutely it. But it does really a nice job for us. And this is certainly one of the strengths of this methodology. It's very, very efficient. We have to, of course, detect these compounds. When all is said and done, they elute from our column. We've got to have something that measures them. And so we'll go through each of these steps and show you a little bit about the equipment, a little bit about how that process goes. This is a simple schematic of the major parts of a gas chromatogram. What we need over here is we've got to have some kind of a mobile phase. And so we'll have a compressed cylinder of mobile phase, most commonly helium, but maybe hydrogen or helium. So we need a flow controller. We need to control how fast our mobile phase is going through the column, right? So a flow controller, how fast is our mobile phase coming in? We've got to have a way to get our sample in there. And so we're typically going to take a syringe, a nice small syringe. We're going to go ahead and poke it down through a rubber seal into here. And this is probably going to be 250 degrees centigrade. So that's usually hot enough to make things go poof, basically vaporize. So they get vaporized in this gas stream. Then goes through our column, eventually comes out, and we have to have some kind of a detector over here. And then, of course, we draw things on our screens, we do data collection, and so on. So that's kind of a simplified version of the parts and what they do. The next one shows a little more detail, so it's be a little more realistic in terms of what we need. So here's our mobile phase. We typically call it a carrier gas. I suppose it carries our sample. I never did think about why they call it carrier gas. That's our mobile phase. So, okay, that's going through the pathway that we mentioned. Here we have we have air and hydrogen. And what this is for, if you look at where this goes over to our detector. What we're going to do most commonly is as things come through our column and get separated, we burn them. And we burn them in a hydrogen flame. So I need hydrogen for the combustion, and I need air to help that hydrogen burn. So basically, I'm going to burn my compounds here. What does burning do? It creates an awful lot of ions in here, and I've got a nice electrical potential up here. And so I measure the flow of electricity across the flame. My flame is carrying the current. If there's no ions, nothing burning, no current flows. If we have a lot of organic material coming out here, looting out of this column, and we're getting burning here, then we start carrying electricity across that flame. That's our detector, flame ionization detector. We've got some other stuff in the whole thing. We put our column inside of an oven. We take advantage of temperature in terms of our separation. It's one of the things that makes this such a darn good technique is we use temperature, boiling point, for separation, and we use affinity for that column phase inside. So we've got two means of separation: temperature, volatility, and interaction with our phase inside here. So that's a little better view of it, of this particular process. Looking at some of the parts, gases. The gases are high purity. We talk about maybe detecting 10 to the minus 14th grams of a compound. 10 to the minus 14th grams isn't much compound. And so we have to make darn sure our gas doesn't contain impurities. Otherwise, what are we going to measure? We're going to measure impurities from our gas. Not a very good deal. So we need a really high purity carrier gas or mobile phase. And that's absolutely essential. Clarity here. And as I said, our mobile phase is typically helium or hydrogen. And this is really an important decision. We'll talk more about that a little bit later. So that's our mobile phase, either helium or hydrogen. That's what goes through our column, gets our separation. And then, as I said, we need something perhaps as a detector gas. So we've got this detector at the end. Does that detector need a gas? Some do, some don't. Mass spectrometry doesn't need a detector gas. Thermal conductivity detector does not. Fourier transform infrared does not. These guys, we don't need any gases to make them work. But when we talk about this flame, you bet. I need air, I need hydrogen. And by the way, this is the most common detector, this flame detector, that is used in our field, so the flame ionization. But there's some other detectors, specialized detectors. Some need a little bit of oxygen, some need some methane. But normally, we're looking at flame ionization, so you'll typically see 3 tanks there. The carrier gas, mobile phase, hydrogen, and air. That's our gases that we need. A couple of things you really have to remember, and the second one's probably the most important, so we'll start with number 1. Pressure regulators. Yep.
So your detector gas and your carrier gas can be the same thing?
They can. I can use my hydrogen tank, and if you come into our laboratory, we've only got a couple tanks. Actually, got 3 tanks. We have hydrogen, no helium you'll find in our lab. Helium's expensive. It's big bucks for helium. Hydrogen is cheap. Also, hydrogen is cleaner, and there's some other advantages to it. People don't like to use hydrogen because they're afraid of it blowing up, exploding or something like this. You know, somebody making mistakes someplace and allowing your instrument to fill up with hydrogen, opening up the door and blowing the place up. It's really hard to do that. I'll vouch for it. We haven't blown one up yet, and I've been in the field a long time, and we would have if it were possible. You know, there's a very limited area or concentration range that you can actually ignite hydrogen. It has to be exactly this much and not that much. And so there isn't a risk with hydrogen, not what people are worried about. And so we take a different choice. We use hydrogen for that purpose. So our pressure regulators, we got to control the pressure flow through this system, the volume of gas and the pressure on that gas. And we really have to have them clean too. Like I say, if we're going to detect as little as 10 to the minus 14th grams of things, we can't have dirty regulators. We can't have regulators with rubber rings inside of them or seals and this kind of thing. They're precision. They're precision instruments, high purity, high quality parts that go into these regulators. And like I say, they are sensitive precision instruments. And when you run this type of equipment, you will actually control it either by the computer or you'll do it manually. If you do it manually, we always tell people, don't keep on turning until it stops. Your gas is going to stop before that. If you turn it until you stops, you're going to crunch my regulator. They're very delicate instruments. So now here's where we put our sample into the system. We got several different ways of putting your sample into the system. I should have talked about initially a very, very simple one. This is our injection port. Here's our mobile phase coming in, so hydrogen or helium. This is a rubber septum, or a silicone rubber septum up here. So our gas comes in here, a little bit goes out here, and I'll explain why. The vast majority comes down here. So we put a syringe down here, our needle's about this point. We push it down, we get our sample put in here. This is hot, 200 to 250 degrees centigrade. It goes poof, and then it gets pushed down into our system for analysis. So a very simple system, hot, simply to vaporize the sample. We can make modifications to this because you'll see something like a word up here, purge gas. So we do allow a small amount to come right back here and go out a vent into the room. Why? Because that piece of rubber, silicone rubber, sitting at 250 degrees centigrade, it's going to also be giving off impurities. So the impurities come down here and they get washed out. So they get carried out. So that's our whole purpose here, keeping impurities from coming down into our system and thus analyzing junk. There's also a split exit from this. So we might have 50 mils per minute of gas coming in here, coming down this tube, coming down here. But we got this tiny column, a tiny column. That's if some of you have even seen it. It's 0.25 millimeters in diameter. That's a tiny column. We can't get 50 mils per minute through that. And so there's our small column down here. It's very much of a restriction. So we get 50 mils per minute coming in here. Some of it just gets split out. It goes then outside of the tube and goes out the exit. So really what we inject, some small portion of the amount we put in, actually gets analyzed. The vast majority of the sample gets split and discarded. Well, why do we do that? It sounds kind of wasteful, but there's various reasons. We want a high flow through the system, so we vaporize our sample. It comes down here, some goes in here, and the rest gets out of here quickly. We don't want this sitting here, over time, keep on feeding the column, feeding the column, feeding the column. Our peaks get broader, broader, broader. I want to go ahead and make my injection, whiz this through, take a little segment of that, and do our analysis. So it just keeps this clean. It doesn't allow things to build up in here. It keeps it clean because this is feeding our column down here. Also, this is a tiny column. There isn't much stationary phase. If I put much material in that, I flood it. I swamp the whole thing, and my separation ends up being very poor. So I'm decreasing the amount I'm injecting. I'm keeping it clean by having a high flow through. Most of it gets dumped. So that's what we call a split injection. We make our sample, we split it, and only a portion gets analyzed. There's other types. So split, yep, that's what I just mentioned. I'll show you split less. In that case, as it sounds by default, I'm not splitting it. I'm dumping everything on my column. But I have to have some way to still keep it clean and keep things moving, which we'll see. There's on column. That's a cold injection. So I think I've got the next two here. And there's all kinds of other versions on this. So it's some innovations along those lines. But the big one by far is number one, split. The second big one in popularity, use, is split less. And this is third. And they tend to be minor. So 1, 2, 3 in terms of importance. So now we see a little more complicated view of what I just explained. How's that? So my gas cylinder is over here. So I have my hydrogen, helium gas cylinder over here. I got a flow controller that I can control and say, I want 54 mils per minute of helium or hydrogen coming into my inlet. 3 mils is going to go that way. As I said, this keeps any garbage up here from coming down here. It's going to come here and go out there. So if 3 mils go here, 51 go down the center here. Under the right conditions, the size of the column, length of the column, it gives enough restriction such that only 1 mil per minute of this ends up going into our column. So that would leave 50 mils per minute coming out here and going out the vent. So 1/50th, if there's 51 mils coming down here, only 1 goes here, 50 go there, only 1/50th of my sample gets analyzed. 49/50ths go out that vent. So that's a split injection. When we do a split less, we do it somewhat different. We'll set it up in the same way. 54 mils per minute come into the system. 3 mils go out that way. That's exactly the same. So 51 are coming down here. But let me see if I got a next one. No, I don't. Okay. In this case, our 51 mils per minute are coming down here. But I shut this off. I absolutely keep anything from going out. So I got 51 mils per minute trying to get down here. And where much of it can go, at least a portion of it, more of it, can get onto this column. So what I'm doing is pressurizing this, forcing more into the column. I wait a few seconds, and then I flush it. I get rid of it. I open up this valve, and everything goes out. It's just a way to put more sample onto or into your column in a split less. So pressurize a little bit. And the other way, I just went out. This way it goes, okay, let's squeeze a little bit in. Now let's flush it. Flush it out if that makes big sense to you. The on column is where I take a syringe that has a long needle, the one you wouldn't want to get a shot from the doctor, believe me. And so you have a septum up here with a really long needle. And this needle will go through a little valve here. And so the needle can be put down here, way down into our injection port. And so this is inside the oven of the gas chromatograph. It's not in the real hot spot. This isn't really heated in this case. So we inject our sample here into our column instead of injection port. We start warming up the column. Eventually our sample vaporizes and moves on its way. Why would we use this? Some compounds aren't stable to heat. And so if I put them in 250 degrees centigrade, I may deteriorate those compounds. They may be destroyed. So this is a sensitive way. I'm not subjecting my sample to heat. I'm putting it just down in the column where it might be 40 centigrade. Then I'm starting to warm it and slowly let it evaporate. Okay, this is the columns, and I smile at this in a sense because at one time all we used were packed columns. And so we would have columns like this, stainless steel columns, quarter inch in diameter, something like that. They'd be hollow, and we'd pack a granular material inside of it. So I would take an inert granular material, I would put a coating my stationary phase, I would coat on these tiny, tiny particles, and then put a little glass wool in the end and pack this with this inert material that has my coating inside. Put another glass wool, and that was my column. It's really not very efficient because when you think about packing granules into here, there can be all kinds of different flow paths, restrictions. Some parts may be packed a little more than other parts. And so we really didn't get good resolution, good separation with this. What we do instead is we actually go for an open tubular column. So here's my glass column. Here's my stationary phase. I've chemically bonded on the inside. That may be half a micron film thickness on here. So I put half a micron of my stationary phase on the inside of this very, very small column. Tremendously efficient for various reasons. And so we tend to use these now. So again, I would think Cindy probably showed you the column if you've done that laboratory. You had a chance to look at it. Tiny columns, they're glass, but kind of neat. They're really pure glass. And you can take and tie them in a knot. You're not used to taking glass things and tying them in knots. But they're so strong and so small that they end up being very flexible, which makes you happier too. They're fairly durable in that sense. Nothing's going to happen to these guys. So that's our primary open tubular. We can actually go ahead and put other things. We can chemically bond other things, some granular material on here on the inside. But we don't tend to do that. That's the poorest layer open tubular. Now I'm putting stuff, granular material, and chemically bonding it inside the column. This is the most efficient open tubular columns. The glass does have a coating on it. So there is a coating on the outside of the glass. It is pure silica. There's a few parts per million impurities. It has a melting point of somewhere around 2,500 degrees centigrade. It's like melting a pure quartz rock. And so very strong, very inert glass. Tiny diameters, 0.1 millimeter up to 0.53 millimeter inside diameter. Tiny columns. Length can be anywhere from 1 meter to 60 meters in terms of length. And you just kind of wind them up, wind them up, wind them up for up to 60 meters. And we can put a number of different coatings inside, number of different stationary phase on the inside of that column. And they're fairly thin coatings. So you think about 0.1 micron film thickness up to 5 microns film thickness. That's a thick film. 5 microns is a thick film. At one time, when we were doing pack columns, we really had to depend upon that coating, that stationary phase, to do our separation. The rest of the whole system wasn't very efficient. The pack columns, poor flow properties, and so on. So we had to have all kinds of different stationary phases to try and get something that interacts properly with things flowing through. But today, we have such high efficiency. Instead of having over 200 different liquids we might put inside these columns, we got probably a dozen materials. And so this high efficiency permits us to limit the materials. So a dimethyl polysilicone is our most common column. It's just a polymer of silicone, a silica polymer. We've got then some polarity put into our column. This is very nonpolar. We start adding cyanopropyl groups through our column. That makes it a little more polar. It's going to like polar compounds better. It's going to give us a little different separation. It hangs on to them. And so we kind of get more polar, more polar, more polar until we get down here to the carboax. That's actually a carboax column. I think that's what you're using for the fatty acid separation. Fatty acids are fairly polar. You want to have something your fatty acids react with, a polar column. And so when you want to separate nonpolar compounds, use a nonpolar column. You want to separate polar materials, you use a polar column. Question is, how to make a choice, right? So we don't have things to pick from. Well, we have a dozen different types of columns to pick from. And so the question always is, what should we use? What should we start with? And the first thing is go ahead and look at published work. That's the simplest. There are very few things in life that haven't been studied by someone somewhere. And that's, of course, a wonder of the internet, permitting you to find this kind of information. So we can look for journal articles, what's been published. We can look at internal work. Oftentimes companies, if you're doing this kind of work, there's probably somebody in a company that's looked at this before. So what do you know from inside the company? Intuition, well, gosh, I know what I want to separate as polar. I'd better use a polar column. Or maybe I use the solvent extract with hexane. I'm going to have nonpolar stuff. Oh, I better use the nonpolar column. So there's always the idea, intuition. What do you think works? No idea. That happens too. I had a person bring a piece of the drywall out of their home. They're carrying it into my lab. He said, my wall stinks at home. Could you help me with this? You don't have much of an idea what that might have been. How's that? A cat, dog, who knows? And so in that case, if you have no idea, what you do is you simply take your nonpolar column, extremely durable. You can heat those things up to 400 degrees centigrade and they still hang in. So they're going to be durable. They probably give you separation. You start with that. Your more polar columns are not very durable. So you start with something that's robust, and then you back off if you don't get separation and try and go more towards polar columns. Well, if we look at different types of chromatography, what do we take advantage of for gas chromatography? Absorption chromatography. You've studied the basic types of chromatography, right? Absorption and all these other ones. So we're looking at typically a surface phenomenon. So there's a surface reactivity on your particle. Your analytes will have some interaction with that surface of the particle or surface of this coating that I put on. Molecular exclusion, remember what that is? That's a separation based on molecular size. If I'm interested in separating helium, argon, nitrogen, oxygen, they're all different size molecules. I use size exclusion for that. So separate by molecular size. Partition, remember that is, you're partitioning into an extracting solvent. That's my coating on my inside of the column. And so my analytes are actually going to dissolve in this coating, come back out, move with the stationary phase. I'm sorry, the mobile phase. Stationary phase doesn't move much. And so go ahead, get absorbed in and out. And that's what gives us our separation. But number 4 is what makes us do well. This is by far the most efficient type of chromatography you'll deal with on a normal basis. Liquid chromatography is in the dark ages in terms of separation efficiency in comparison to this. And one reason is we use 2 different techniques for our separation in gas chromatography. We use this, or this, plus volatility. Is it volatile? Does it really want to be in the gas phase because it's going to be vaporizing? And you don't get to take advantage of that in liquid chromatography or other methods. So the idea of looking at boiling point, volatility, put together with this makes an exceedingly powerful technique for separations. Column coatings. I think I probably mentioned this. They range in polarity. Most polar is the carbox. That's what you're using for fatty acids. Non-polar, silicone-based. And every company, of course, names them as they want. And so they'll make their product, and it'll be Hewlett-Packard such and such, or it'll be an Agilent such and such, or Waters. And so they can be exactly the same material, but a company chooses to call them their own name. Column, we do put these in a column oven. Otherwise, how can I take advantage of this difference in boiling point? And so we do put our columns inside of an oven. The ovens we can bring down to about a minus 60 degrees centigrade. That stops most things. There isn't much volatility at minus 60. So that hangs on to most things. Only a few things are still a gas at that temperature. So we can really slow down, stop things. Then we can gradually warm our column. Oh, now those that want to vaporize, want to volatilize, now they move into the gas. Heat it some more. Now something else wants to go into the gas phase. So we temperature program to bring this up to take advantage of this boiling point or volatility. We do have this detector, as I said, and so we make our injection in the system, and we monitor, of course, time. What really we're measuring is flow, but we simply use time. Typically, that's an easier thing to conceptualize. So we're going to go ahead and monitor our signal. Terrible looking peaks. I have to change this for next year. You know, if I got a peak like that in gas chromatography, I'd throw it out and I'd tell a grad student to go back and try again. Okay, sorry about that. Because in our world, you want them to come out like this and be maybe 2 seconds in length or time frame, not minutes. So anyway, notice we even go slowly with this. So what are we doing? Of course, we're measuring compounds, and so we measure the area under this peak, and that's proportional to the amount of material that's present. So there is that relationship. The bigger the peak area, the more compound. In liquid chromatography, you'll commonly look at the height of a peak. In gas chromatography, we typically look at the area of a peak. In liquid chromatography, you have better control of your injection, better control of some of your parameters, and so your peaks typically have very common shape, and they'll say pretty easy to measure the height. But in gas chromatography, your peaks sometimes are broader, narrower. If they're broader, of course, they're shorter. If they're skinnier, they're taller for the same area. So we have to measure area in gas chromatography. What's that?
We do area as well because the column changes efficiency, so the height is not always.
That makes sense, but it's been slow in coming. Yeah. I have fun. We harass each other about liquid chromatography, gas chromatography. So yeah, well, we know. We do have fun at it. They both, obviously, they both have their place, and they sometimes overlap. And I can't argue with liquid chromatography justifiably. I can tease a lot, though. Anyway, so detectors. Many types of detectors, just like we got different ways of introducing our sample, we have different ways of detecting things when they finally get out of our column and form a peak. And we're just going to take a look at the most common types of detectors. This is the first one. This is the first detector that was built for a gas chromatograph. And so it's called thermal conductivity, heat transfer. Oh man, that's a lead-in to food processing, isn't it? Okay, we're looking at thermal heat transfer as we go through here. And so we have our column separation. We've got our mobile phase coming out, flows through this detector. And so if we're using hydrogen or helium, we'll have a certain heat loss. This is a filament, electrical filament. It's hot. And so this gas will cool that filament to a certain amount. And as the temperature changes, the electrical resistance changes. So I'm measuring the electrical resistance across this filament as it changes temperature. If there's just hydrogen or helium, we get a certain heat transfer. If I start getting an analyte in there, hey, guess what? I change my ability to transfer heat. I might transfer more heat when I've got some carbon-containing compounds in here. So really, every time an analyte comes through, changes the heat transfer, cools that filament, decreases the resistance, and I get electrical current flow. So I'm measuring how much cooling or we get of this filament. And this is just the example. There's nothing here, and this has an analyte. It's the idea that the triangles are an analyte coming through. So different resistance to electricity. Characteristics give you the high points of these detectors. Do we run to 230, Pam? What to what? 1240? Oh, shortchanged. Okay. Anyway, I am teasing, by the way. I didn't know. Specificity. I was looking for some of you to faint or something. No, Gary. We get out at this time. So anyway, Specificity, very little specificity. You'll get a response from anything, any compound, water, gas, whatever that's going through that column, because you change the heat transfer. So the only thing it won't detect is the carrier gas, the mobile phase. If you would put more helium in there, it wouldn't detect it, if helium's a gas, but it'll detect anything else. That's the beauty of it. It's called the universal detector. You don't get it without paying for it in some other way. Sensitivity, you need a minimum of 10 to the minus 7th grams of analyte flowing through that detector per second, 10 to the minus 7th, or else temperature doesn't change enough. So you can't detect things if they're less than this amount. That's poor. You might say still 10 to the minus 7th. In LC? We'll talk about that. And it's poor.
No, I meant for the student, because sometimes I ask questions which is more sensitive than GC or GC.
Oh, of course, a GC.
Yeah, I like much
You got the answer for that? Okay. Okay. We'll get to some better ones, so don't worry. I'll have to talk to her about this. Anyway, 10 to the minus 7th grams, and that is poor by our standards and probably by LC. And also linear dynamic range. If you have this much of a compound versus that much, is it still linear response as you change concentration? And that's linear, gives you a linear response, only about a 10,000-fold change in concentration. And you might think 10,000-fold change in concentration in a given sample is pretty good, but it really isn't. And so we're limited here, but we have the wonderful ability for a universal detector. Here's my flame ionization column, or detector, as I said. So this is our column mobile phase coming up here. Mix a little bit of hydrogen in there, have a little bit of air coming in. Here's where we burn our sample. Here's our electrode here. So this is grounded. This is 300 volts. And so we look at the flow of electricity across that flame. Very simple detector. Anything that's organic will give you a response to this. If it's an organic compound, it will respond. If it's non-organic, you will not get a response to it. So specificity, organic compounds, that's what we deal with in foods for the most part, right? Organic compounds. Now we're down to 10 to the minus 12th grams per second. That's getting a little better. So pretty good detection limits. And so that's good for most organics. We're quite happy with that. It will be linear. You can have two compounds differing by 10 to the 6th or 10 to the 7th, and it will give you a proportional response. So quantitation tends to be easier. There's some alternatives of that we can make this nitrogen selective, but we won't deal with that now. Electron capture has been used for a lot of the pesticides. They happen to be, many of our pesticides are electron capturing molecules. They can be halogens, chlorine, bromine particularly. And so chlorine, bromine love to attract electrons. So in this case, what my detector is, I've got a reactive foil, a radioactive foil on the inside, typically tritium or nickel-63. So I've got radioactivity. As it sits there, it's decaying. It's giving off electrons as degradation products. So I'm always giving off electrons that get collected here. So I've always got an electrical current coming out here. If a compound comes through here and it likes to absorb electrons, my current decreases. My compounds have absorbed my electrons, and so my current flow decreases. So again, fairly simple detector. Now we're down to 10 to the minus 14th grams per second. So we're getting down pretty low in terms of, pretty good in terms of sensitivity. Not so linear. It is selective, halogens, conjugated carbonyls, nitriles, and a few other. No response with most organics. So that can be a blessing or not. If you want to measure halogens and you've got interference from the organic compounds, it doesn't see organic compounds. You don't have to do as much sample cleanup or sample prep. They do have temperature limits. Yep, you don't want the radioactivity coming out in the laboratory. Not a good deal. This is, I think, probably, we'll see if this is the last one or not, but chemiluminescence, that's something that we make use of a good deal. We've got a reagent gas that comes in. There's a flame ionization. And so here's your effluent from your gas chromatographic column. So your compounds end up being burned in this flame with oxygen. And what they do, of course, you know that from atomic emission, right? Spectroscopy. Different atoms give off different wavelengths of light. And so what I've got here is I've got a filter that filters out all light except for maybe sulfur, except for maybe some other molecule or atom, I should say. And so this is more or less sensitive to specific atoms being present. And we're really interested in sulfur. This is a very low low threshold for sulfur, and sulfur is very important to flavor compounds. So this is a very important detector for us. Very selective. It only detects sulfur or phosphorus. That's a little bit about showing a little bit more about it in the sense you burn your flame here. Here's your photomultiplier, PMT, photomultiplier tube that's measuring the light, and here's your filter. There are other detectors when you transform infrared mass spectrometry. We'll start with mass spectrometry next time, an extremely powerful tool for us. And so we'll start at this point. If there's any questions, ask them or come up afterwards. Happy to deal with it. It's so much fun, isn't it? Oh, you're not gonna try to defend HPLC, are you?
No, you know, it has